In this video I will show you in a quite unique experiment what the term electrical resistance actually means. I will build two resistors of varying length from a piece of Play-Doh and two copper coins and then use a multimeter to measure if the resistance value changes as predicted by the theory. And I will also show you how to construct a current voltage characteristic and how to use it to see whether a material obeys Ohm's law, and especially if we send half an amp of current through it. My name is Andreas from the Fearless Engineer, and here we go. In the last video on Ohm's law, which you can find up here, we have seen that the resistance value of a conductor depends on the conductor material and on its geometric properties, which in case of a cylinder are of course the cross-sectional area and its length. Both quantities make immediate sense because imagine an electron traveling through a long conductor, a lot of its kinetic energy and thus voltage is converted into other forms of energy such as heat. And if the cross-sectional area is reduced at the same time, then the number of collisions between electrons and the atomic structure of the conductor occur more frequently, which means that even more kinetic energy is converted into heat. And this means that a long and thin conductor must have a higher electrical resistance than a short and thick conductor. And that's exactly what we want to try out in this video here by building our own resistors out of Play-Doh and out of two copper coins. And in the first part I'll show you how to actually construct the resistor and its housing, and in the second part we will then connect the resistor to a voltage source and make some measurements with different voltage levels. And thirdly, in the last part, we want to find out how large the resistance values are in each case for each voltage level, and we also want to check whether Play-Doh is an ohmic material, which means that the resistance value should be totally independent of voltage and current. So let's do it. In our derivation of Ohm's law from the last video, it's very easy to see that the length L is proportional to the resistance value R and that the cross-sectional area A is anti-proportional to it. And in order to verify this in the experiment, we need a resistor with a very simple structure, ideally a cylinder. And the problem is that Play-Doh is an elastic material, and if we simply just connected two wires to it, the contacts would shake loose very quickly and the resistance value would change dramatically within one experiment even. So in order to solve this problem, we need to make an invention here. So I decided to ransack my children's playroom a little and I found the following items. An angle bracket made by Fischer Technique from which we will build the resistance housing, then two 1-cent coins with a short piece of double-sided adhesive tape attached to them, and these will be the contacts of the resistor to which we will connect the power supply. And then there is a small spring with which we can build up a certain amount of pressure so that the coins will be pressed firmly against the Play-Doh. And if we just wouldn't do that, the resistance value is not going to be stable and the measurements would fluctuate a lot here. And finally, we also need a pot of Play-Doh. So here we go with the construction of the short resistor. The first thing we do is we fix two pieces of sticky tape onto the coins, and then we pull off the protective foil, we take the spring and press it firmly onto one of the coins to create a stable bond between the two. And then we stick a third piece of tape in one of the corners of the angle bracket, pull off the foil and press the free side of the spring firmly against it. And now we have already finished the first connection of the resistor, and as soon as we insert the Play-Doh cylinder in a few seconds, the spring will press the copper coin firmly against it, creating a stable contact over the entire cross-section of the Play-Doh. And next we stick the second copper coin into the other corner of the angle bracket as our second contact. Okay, and that's it. We now have finished the casing for the short resistor. When it comes to grabbing a pot of Play-Doh, it's my impression that the resistance strongly depends on the brand you use and even on the color you take. And also, it's important how long the Play-Doh has been exposed to the open air and how much moisture it still contains. So if you should choose to conduct this at home, this experiment here, you might get different results from the ones we will see in this video, but that's not a problem because it's about the basic principle and the idea behind a resistor and not necessarily about reproducing the same values. And for our experiment, we take a thick piece of Play-Doh and we roll it into a cylinder. And once we are finished, we briefly press the casing with the two coins against it so that two imprints are created in the Play-Doh. And now we take a sharp knife and just cut off the cylinder a little bit next to the two imprints so that the resistor is a little bit longer than the distance between the two coins. This is important because the spring has to build up a certain amount of pressure to create a decent contact, and this only works if the cylinder is long enough. And now we can compress the spring with a pair of tweezers and simply push the resistor body into the case. And that's it, we are done. And next we have to find out both the length and the diameter of the cylinder. And we can easily do this with a caliper, and for the short resistance I can read a length of about 37 millimeters and a diameter of about 16 millimeters. I have built the case for the long resistor in exactly the same way as for the short one, and we can just fit the cylinder in exactly the same manner. First we roll it out and then we press it against the coins, cut off a little longer and push it into the housing. The length is now about 97 millimeters and the diameter is about 15 millimeters. So the long resistor is about 2.5 times as long as the short one, while the diameter has remained about the same. So next we want to integrate our resistor into a simple circuit, and for this we need a power source, an amp meter and a voltmeter. And the voltage source on the left, for example, consists of two parallel lines, one of which is longer than the other. And the shorter line here represents the negative terminal, that's the side with a surplus of electrons. And to the right of it you can see a current meter and a voltage meter drawn as elongated rectangles reading 0 amps and 0 volts of course. And as soon as we take a look at the actual setup, the three components will be arranged exactly as shown in the circuit diagram here, next to each other. And above the voltmeter in the upper right corner you can see our resistor as a small rectangle with two long legs. And once we connect components in the circuit here using some cables, we simply draw a line from one connector to the next in the circuit diagram. And in this video here, we just for simplicity, we ignore the fact that cables also of course have a certain resistance, and we assume that they connect the components in an ideal way. So here you can now see three of the components in our circuit. On the left is the voltage source, in the middle is the amp meter, and on the right is the voltmeter, which you might remember from the last video about how to construct a lemon battery. The link is coming up in the cards. And first we connect the negative terminal of the voltage source to the input of the amp meter, and in the circuit diagram we draw a corresponding line from left to right. And then we connect the output to the input jack of the voltmeter. And then we use a crocodile clip to connect our homemade resistor to the same cable that connects the voltmeter to the amp meter. And now another crocodile clip from a red one from the other side of the resistor is connected to the red terminal of the voltmeter, and the two are now connected in parallel, as you can see in the circuit diagram. This is something which we will discuss in future videos, parallel and series connection, but for now we just can see the two connections are shared between the two components. And from there we go back to the voltage source. And the circuit is now closed and we can start taking actual measurements here. Now we successively set the voltage source to the values 2 volts and 4 volts and 16 volts. That means we double the voltage from measurement to measurement. On the bottom right you can read the current flow, and on the top right you can read the voltage drop across the resistor. And the value differs slightly from the preset voltage from the power supply, which is partly due to inaccuracies in the meter and in the voltage source, and partly also due to hidden resistors within the circuit, which for example could take place in the current meter or in the wires. And if you look carefully at the two displays, you may have noticed that almost the entire voltage drops across the resistor. And when we talk about Kirchhoff's laws in one of the next videos, let's take a look at why this is the case more closely, but for now we only take note of it. And what you can also see here is that the current through the resistor steadily increases between measurements. And also the current always fluctuates a little bit, which is probably because Play-Doh is not a very good resistor material after all. And in the last measurement with 31 volts, by the way, more than 200 milliamps will flow through the resistor, and that's quite a lot of current, which is definitely more than you should safely touch. For the second row of measurements we now disconnect the short resistor and connect the long one. And apart from the value of the resistor, nothing changes in the circuit diagram. And now we run the measurement series with the three values again, first with 2 volts, then with 4 volts, and then with 16 volts. And I've written down the values from the first round of measurement, and we will compare them with the new ones in just a few seconds. But what you can see here right away in the 16 volt measurement is that the current of about 230 milliamps, which we saw with the short resistor, has now dropped significantly to less than half. Okay, we have finished with the actual measurements, and now it's time for the evaluation part. And first we want to find out how big the resistor values of our Play-Doh contraptions really are. And if we can easily find that out using Ohm's law and the voltage and the current measurements we have just taken. The table you can see here shows the values for the short resistor, and in the gray column on the left you can see the voltage, in the blue column in the middle is the current, and on the far right in green is the calculated resistance, in which is the ratio of voltage and current. And in the diagram on the right, resistance and current are plotted against voltage. That means the higher the voltage, the further right the respective measurement points lie. And the first thing you notice is that the resistor value is not identical between the measurements. It ranges actually from 212 ohms at 2 volts, and it goes down to 51 ohms for 25 volts. And in the diagram you can also see this graphically. The less voltage is applied, the higher the resistance value is. And from the blue curve you can also see that the current behaves accordingly to this. And the more voltage we apply, the lower the resistance, which results in an exponential increase of current flow. And things actually look very similar with a long resistor here. The current flow also increases exponentially with increasing voltage levels, which leads to the conclusion that resistance value is significantly higher at low voltage levels than at higher voltage levels. And by looking at the curve shape, we can also see that Play-Doh is clearly not an ohmic material. And if you have watched the last video, you already know why. For a purely ohmic material, the resistance value remains constant over all voltage levels, which results in a linear relationship between voltage and current. And we can clearly see from the green curve here that this is not the case for our Play-Doh resistors. And finally, lastly in the video here, we want to take a very brief look at the electrical conductivity of Play-Doh. We have already seen that the formula for resistance contains geometric properties, that means the length and the cross-sectional area, as well as material-dependent quantities, which are grouped into the so-called conductivity sigma. And we have seen before that sigma includes the free electron density as well as an indicator for electron mobility, which describes how easy the charges can flow through a specific material. And what we want to do now is to calculate sigma for the Play-Doh we have been using in our experiments, which can be done by simply dividing the length by the product of cross-sectional area and resistance. And the formula can be seen in the orange box down here below. And please note that all length units have to be converted into meters just to ensure that the unit of sigma is amps per voltmeter. And as soon as we're done, we can plot the results into the diagram here, where you can easily see that the conductivity is not constant over the voltage levels. That means the material changes its properties with increasing current flow. And it's also interesting that the two curves for the short and for the long resistor are not identical here, although I have eliminated both the length and the thickness bias here. So, final conclusion, after all, Play-Doh to me does not seem to be a very good material for a resistor, even though I really enjoyed the experiments with it. Now that was quite a lot of information on electrical resistance and on conductivity. And what you should definitely take along is the basic idea behind it. We can use the geometry and the material properties of a conductor to control how much current flows at a given voltage. And here in the video we have only changed the geometry, but if we would have changed the type of Play-Doh as well, this would have led to similar results here. And in the next video we will take a look at actual resistors used in electronics, so we can soon start building our first electric circuits. Oh, and also you can find all the slides and all the circuit diagrams from my videos on my website at thefearlessengineer.com for free. The link is coming up here in the banner. So have fun and see you next time here on The Fearless Engineer.